In part 2 of chapter 3, we'll look at the idea of pure substances and mixtures and the idea of physical and chemical changes. Now, we're going to take a very brief view of the idea of dividing matter up into pure substances and mixtures. We're going to condense it down basically into this slide. So when we're talking about matter and we want to classify that matter, you can have one of two groups. You're either looking at what is known as a pure substance, or you're looking at a mixture of substances. Okay, now breaking that down further, a pure substance is going to be composed of only one type of atom or one type of molecule. So if it's composed of only one type of atom, that is what is known as an element. So the example that it's showing here, these pieces of copper, these little pieces of copper wire, are composed simply of copper atoms that are arranged together in an orderly fashion. You can also have a pure substance that is made up of only one type of compound. So a compound is going to be made of two or more elements that are put together in fixed definite proportions and are held together by chemical bonds. And then those molecules are repeated over and over within the compound to make up a substance. And the example shown here is sucrose, or table sugar. Some of you commented on that in your discussion assignment, and you can see, according to the figure here, this is a molecule of sucrose, so C12H22O11, and it's a repeating orderly pattern over and over, and then these molecules come together to make a crystal of sugar or a sugar cube. Now, if you have more than just an element or a compound, if you have more than one compound or more than one element and compound combined together, you're looking at the idea of a mixture. Now, with mixtures, you're looking at different substances that are not chemically bound together, but they're simply mixed together in a physical manner. So, for example, and then you can subdivide mixtures into either homogeneous, where you cannot see the separate materials making up that mixture, or you can have a heterogeneous compound where you can see the individual components of the mixture. The example they're showing here of a homogeneous mixture is tea. So in the tea, we have water. We know that we start with water, and then we've brewed it, and we have different molecules or compounds from the tea that are going to brew out into the water. You may add a sugar cube to that, so you may have a sucrose molecule in there, but you're going to have separate substances in there. Now, I can't see those just looking at the cup of tea, but I could separate those out. So for example, if I were to leave that cup of tea sitting around for several days, or if I were to put it on the stove and heat it up, I could boil the water off, and what I would have left behind is a mixture of sugar and the components in the tea. And then there are other things that I could do to separate those components. So I can easily, with physical means, separate the components in a mixture. And we'll talk about the difference between physical and chemical separations in the next few slides. Now, in a heterogeneous mixture, like they're showing a mixture of oil and water, you can easily see the different substances making up the mixture. So here we've got molecules of oil, we've got molecules of water, and they do not mix because of their different chemical properties. Lots of examples of heterogeneous mixtures out there. If you eat a pizza, if you have a pepperoni pizza, you can very easily see the components. You can see the pepperoni, the cheese, the sauce, the crust. If you eat Lucky Charms, you can easily see all the different pieces, the marshmallow bits in the cereal. Heterogeneous mixtures, very easy to see components. Now, another example of a homogeneous mixture that you may not be as familiar with is milk. Whether you're aware of it or not, there are different components to that milk, and they can be easily separated out. So, for example, if you were to take a glass of milk and pour a little vinegar into it, what would happen? Well, immediately nothing, but if you let it sit over time, you'll notice that it looks curdled. It starts to look spoiled. Or if you just let a gallon of milk spoil, you see that you start getting sort of a mushy solid material. You get kind of a yellowish liquid on there. That's the whey. So the whey and the protein will separate out. It's just a mixture that's bound homogeneously until you do something to interrupt that mixture. Alright, so just summarizing that last slide that you looked at. Matter can either be a pure substance or a mixture. If it is a pure substance, it may either be an element or a compound. If it is a mixture, it could be either homogeneous or a heterogeneous mixture. And just one other point to make. Mixtures can be composed of two or more elements, two or more compounds, or any combination of those. So you're not limited to just compounds or just elements in a mixture. You can have both of those together. All right, so that's a quick summary on the parts of mixtures of matter. All right, now what we want to look at next is how the properties of those different kinds of matter have an effect on the way things react. So we will look at, in this case, physical versus chemical properties. A physical property is going to be one that a substance will display without a change in its composition. So you're not changing the fundamental nature of something based on its physical property, or if it's going through a physical change, which we'll look at in a minute. A chemical property is something that a substance will only display or show when it is changing its composition. All right, so let's look at some examples of what we're talking about with that. If we look at gasoline, if I just open a can of gasoline, or if I'm at the pump and I start pumping gas, I'm going to notice something. I'm going to notice an odor, and it's very characteristic. Almost everyone who drives a car knows what gasoline smells like. That is a physical property. The gasoline is not changing its composition when it exhibits that odor. It's always there with gasoline when some molecules are going to volatilize. So if I'm smelling gasoline, that doesn't mean that the gasoline is undergoing any sort of chemical change. It's not changing its basic nature. If I could capture those molecules that I'm smelling and condense them back down to a liquid, I've still got gasoline. Now on the other hand, if that gasoline goes into my engine, I start the engine and it goes through combustion, when that gasoline is combusted, the flammability of the gasoline, that does change the composition of the gasoline. So if I burn gasoline in my car and then capture all of the exhaust coming out of my car and condense it back down, I no longer have gasoline. What I'm going to find are a variety of other things. I'm going to find a lot of water vapor, I'm going to find a lot of carbon dioxide, I'm probably going to find some other components that were in there, some sulfur, some nitrogen, other things that are in that gasoline. So the process of combusting the gasoline is a chemical change, and that's a chemical property of the gasoline, the flammability of it. So let's go through this idea again with our good old standby water. Water, you will find, is a very constant substance that we'll look at in chemistry a lot. That's just because water has some amazing properties that we'll see as we go throughout the semester. All right, so physical changes, physical properties. When a substance undergoes a physical change, it does not change the basic atomic or molecular composition of that substance. So for example, looking at our water, we know that the boiling point of water is 100 degrees Celsius or 212 degrees Fahrenheit. That is a physical property of the water, the boiling point. So when water boils, all it's doing is changing from a liquid state to a gaseous state, but the molecular composition of both the liquid and the gas is identical. The molecules are the same, it's just the distance apart that those molecules are from one another. Okay. So going from liquid to gas, physical property. So we relate that as boiling or vaporization. So boiling or vaporization is simply a physical change. All that's happening, molecules are getting further apart, or condensing the steam back down to liquid, they're getting closer together. Okay, so just one thing to kind of point out, and the same thing happens with freezing when we go from a liquid to a solid state of water. All we're doing is changing the state of the matter. So when we're going through a change of state, we're going from solid to liquid to gas, that is always going to be a physical change. So keep in mind, in a physical change, the matter will change its appearance, but the basic composition is the same. If we can look at it on the molecular level, nothing has changed there. In a chemical change, however, the matter is changing its basic composition. One of the classics that we're familiar with for chemical change is oxidation of metal. One example is copper. If you've ever seen a shiny copper penny versus an old one that's been sitting out in the weather for a while, you'll see that the copper starts turning green. It gets a green kind of crust on it. The Statue of Liberty is a classic example. When this statue was first built, it's made of copper. The copper was a bright coppery color to start with, but upon exposure to air, it begins to react with the gases in the air. It forms new compounds which turn green. And if we could look at it on a molecular level, we would see it no longer looks just like copper atoms. It's copper and oxygen chemically bound together. Okay, another example of oxidation that we know of, all metals oxidize. Iron, in particular, its oxidation is known as rust. So we talk about a lot of different metals rusting, but really the only metal that truly rusts is iron. Other metals simply oxidize. But rusting or oxidation is a chemical change. So if we look at the nail that we have here, it's an iron nail. As it's exposed to oxygen, we can see in the original part of the nail, we have nothing but these iron atoms neatly stacked together. Upon exposure to air, the oxygen starts to insert itself chemically. It starts bonding to those iron atoms, and it forms what we call iron 3 oxide, ferric oxide you may be familiar with, also known as rust. Okay, so how matter changes in a chemical reaction is the basis of what we're looking at in chemistry. That's where we really start getting into the interesting stuff. When we have an initial material that we call a reactant, and it reacts in some way to undergo a chemical change, and it forms a new substance that we're going to call a product. Okay, so what you're seeing here is the language basically of chemistry, and this is sort of a sentence. I like to tell people that chemistry is a lot like studying a foreign language, and the elements that we have in the periodic table, which we are getting to, by the way, those are our alphabet. So when we learn those, we're learning the alphabet. And then we learn how to take the letters in that alphabet and put them together to make words. Okay, that's going to be our elements and compounds that we saw, our pure substances. So when we build compounds, we're putting letters together to make words. Okay? And then we can take those words and mix them together. So we can take two compounds and put them together and get two other new compounds or one new compound or something. This is writing a sentence. To a chemist, this format is a sentence. It's telling me a phrase. It's telling me something in terms of chemistry. Okay, so we want to get familiar with this format. Reactants do something, they undergo a chemical change to form products. Now, when we're looking at these chemical reactions, or even some physical reactions, physical changes, the difference between chemical and physical changes is going to be seen at the molecular level, the atomic level. We do see something physically happening on a macroscopic scale, but in chemistry what we're interested in is looking at it in terms of the microscopic scale. We want to know what's happening at the atomic level. Physical changes, atoms that compose matter are not changing their fundamental makeup or association. It'll change in appearance, but on a microscopic level, everything is still the same. Chemical change, the atoms are being broken apart and put back together in a different way. They're being rearranged, so we get matter with new identity. Okay. So physical change results in a different form of the same material. Chemical change results in completely new materials. And let's look at some examples of both of those. Here's one example of physical change, and you might think of others. Certainly the ones that we're listing here are not a complete list of all physical or chemical changes. There are plenty more out there, just giving some examples here. If you have a butane lighter, if you know how a butane lighter works, if you could look inside of one, you have a chamber here which holds a liquid, usually liquid butane, and you've got a source, a button that has a flint in it, and you can push that down, strike the flint to create a spark. Now, if you take that lighter and just press this lever here without turning the wheel, without forming a spark, all you're doing is opening the system to allow the butane to come out. So if you were to do that and listen carefully or smell very carefully, you would hear a hissing sound, you would smell butane coming out of that lighter. Okay, so the liquid butane is going to vaporize and form gaseous butane. It's undergoing a physical change, but the molecules here in the container in the liquid butane are the same as the molecules coming out in the gaseous form. Now, what happens if we turn the lever and create a spark at the same time that we press down? Okay, now, when we do that and create a spark, we get a flame. Okay? And so what's happening is these butane molecules in the liquid form are combusting with oxygen molecules in the air. It's undergoing combustion. When it does that, it's forming new molecules, usually carbon dioxide and water molecules. So when we're looking at that, we can see that these molecules are different from the ones that are in here. Now, what it's not showing, you'll notice that red is appearing up here, and there's no red down in the lighter. Well, that's the oxygen in the air. They're not showing the oxygen atoms in the air around it, but that's where those are coming from. So this is chemical change. The molecules inside the lighter are very different from the ones coming out of the flame. Now, there are a lot of common techniques in the chemistry lab for carrying out physical and chemical changes and separations. A couple that are used for physical separations. One is a distillation process. So distillation is the act of boiling a mixture of liquids and taking advantage of the different vaporization rates of those liquids to separate them. So this is a distillation setup that you see here. Here's my flask that contains a mixture of liquids, and I put a heat source under it, a burner. And then what I'm going to do is allow these liquids in here to vaporize. Well, they have different properties that create vaporization at different temperatures, and we'll look at that property in a minute. But not all the liquids are going to boil at the same temperature. They boil at different temperatures. So one of them will boil at a lower temperature. It will come up and form a gas. The other liquid will remain in the liquid phase. Now, what we're doing here is we've created this condenser. It's basically an area of colder temperature. So what we're doing is putting cold water in. This is actually a jacketed two-part condenser here. So there's an inner tube through which the gas can pass. There's an outer sleeve through which we pass cold water. We put cold water at the bottom, we let it come out at the top, and it creates this cooled area, this cooled circulation, so that as the hot gas comes up here and enters into this area, it loses energy, recondenses to a liquid, and then runs down that inner tube and then into what is known as a receiving flask. So whichever liquid is more volatile, boils at a lower temperature, will come through here first. And so what I'll see is this distillation starts, I'll get this drip of liquid, and then at some point, assuming the boiling points of my two liquids are different enough, I'll see that things quit moving over into my receiving flask. I won't get any more liquid in here, and then this liquid will be sitting here. At that point, this should be essentially a pure liquid of whatever boiled first. This may be a pure liquid or may still be a mixture depending on how many liquids I had to start with. Okay, so distillation is a technique that you'll probably see in organic chemistry when you get to that point. Okay, another one that we use, and you'll see this one pretty much right off the bat, is the idea of filtration. And filtration is going to separate mixtures using physical change. So what we're going to do, there's lots of different ways to carry out filtration. Common one is gravity filtration, where you simply take a funnel and line it with a filter paper to trap any solids. This allows you to separate a mixture of liquid and solid. So for example, if you had a mixture of sand and water and you wanted to purify that, You could pour it through here. You have a filter just like a coffee filter. You're going to pour it through. It allows the liquid to come through. The solids remain trapped there. So we'll look at different filtering techniques, both this method, which is known as gravity filtration, and vacuum filtration throughout the semester. Okay, so just a quick summary of physical and chemical separations and changes.